Thank you so much, Kevin. I really appreciate the opportunity to meet with everybody today. Really excited to share with you guys about how we're able to start using agentic AI combined with IoT, industrial IoT, and we're going to walk through that a bit. What does that really mean, and to understand it? And the part of it that's fun for me is last year I did a similar presentation, but it was all about generative AI. And so we're going to kind of compare and contrast what happened in 1 year and how we even accelerated, even going faster and with the technology and how we're bringing it into the industrial settings. So thank you so much, Kevin, for the intro. You gave me a good overview of my background. I have been doing this for several years. I've worked in large communications companies, did 5 or 6 startups in my career, authored several books, and today I have the opportunity and privilege to be the CTO at KMS Technology, where I help guide and shape the directions for the services and offerings we bring. Before I go into it just a little bit, let me just share what we're going to talk about. Just give you just a quick overview of who KMS, what we do. We'll talk about what is the magnitude of the problem that we're wrestling with, and we call it the $3 trillion problem. And then we're going to compare what did legacy IoT or industrial IoT with AI compared to industrial IoT with agentic AI. What's the difference? And we're going to look and deep dive that a little bit. And I'm going to show you how the systems are evolving and how you can evolve your systems. And even though today we're talking about the use of agentic AI in manufacturing, a lot of the design patterns, the reference architectures I'll share today, they are very much extensible to other industries, other verticals, and even within enterprise workflows. Now, the edge is different, but the concepts should transcend into many different areas. I'll also share with you a reference architecture and some design patterns that we see emerging that are being practiced today. I'll show you a high-level approach, and then I'll also show you some of the challenges that we are experiencing, particularly with new challenges that have emerged with an agentic AI approach as opposed to purely predictive or generative AI using IoT data previously. And then we'll end on a case study to show you another example of when it's properly deployed and used, what are the material impacts that you can see by going down this path. So quickly about KMS, we're about 1,300 engineers. We've been in business for over 15 years. Many clients have been with us that entire time. But really what we do, we provide advisory, implementation, maintenance, and operational services as we help our clients to build products, systems, and solutions for them. So we're really an engineering services company. And that gives us a unique opportunity to work with many different companies, many different industry verticals, and it allows us to see a different set of challenges and opportunities that we can, and some of that benefit that we realize we can now bring to our clients. So jumping into it, let's talk about the $3 trillion problem. We've been wrestling with this number, and it depends upon what data set you look at. Some show it's 1.5 trillion to 3 trillion, but what that really means, that is how much lost productivity on a global basis that we're wrestling with downtime of manufacturing. Now, that is a monumental number of just think how much lost, excuse me, how much lost productivity simply because of unplanned downtimes for the equipment. Now, to address this, in the last several years, we've been introducing a variety of different types of AI systems to help address that. But still today, where we are seeing anywhere from 75 to 90% of the AI pilots that are going into the marketplace, they actually don't even make it into production. And we'll talk a little bit about that on the challenges slide. And then we have made tremendous progress in the past of combining artificial intelligence with industrial IoT, but it has been more reactive and it has been less proactive to help take those particularly autonomous actions that could help address issues much, much faster. Now, I've been, as Kevin alluded to, I've been doing this for several decades now. And my first AI engine that I had the opportunity to build was in 1992. So we have been doing this for a very long time. So we have introduced and used AI for a very, very long time. But still, even with all the computer vision enhancements, with the predictive maintenance enhancements, it's helped, but we're still struggling with this unplanned downtime. So that's the problem that we're going after. So and I've been using the terms agentic, not everybody may be familiar with that. I'm assuming our audience today, everyone's fully in tune with our industrial IoT solutions, how we're really gathering up information from the very smallest part of the edge of the network, like sensors, and bringing that into to help us give us insights and help facilitate decision making. So really now what we want to share is, hey, what does it mean to bring agentic AI into an industrial IoT system? So first, let's compare and contrast a bit. Our legacy AI and IoT, in the simplest words, those systems, they will tell you about the problem. I will notify you something is wrong. There's an alert, a threshold gets breached. I'll trigger an andon light. I will do something that notifies the operator that something's went wrong. And so we've built a lot of infrastructure around these reactive dashboards. We were using and started making good headway with using generative AI to give us insights to help on the root causes, but it's still the actions we take are still manual. And we're still wrestling with these fixed set of schedules that are bound by these pre-programmed software systems on a line, and it's just been fixed. So we start thinking about to the right side of the picture, when we talk about agentic AI combined with industrial IoT, what does that mean? Well, now we go into a world where we have autonomous agents. And so the big, big difference is, as opposed to the previous state, I will tell you about it. Agentically, now with AI, we will say, I will do something about it. I will take those actions through an autonomous agent. I will autonomously do self-diagnosis and monitor, and then take some actions dynamically. And a key thing that you'll hear me say today on this, there's a couple different elements that are hallmarks about this, the agentic approach, that it's dynamic and adaptable. And so you'll see in an example I'll show a little bit later what I mean by that. But so an example here would be dynamic load balancing or line balancing between production lines, making systematic changes based upon what the agent is sensing and able to address it. Now, I've used agentic several times. Let's talk about it, how I define it, and how we use it here at KMS to help our clients understand what does it mean when I'm moving from a traditional world of machine learning algorithms, generative AI, and now I'm introducing agentic. What does that really mean? In the simplest terms, you can think of it as a five-stage model. Agentically, the AI, or typically we'll talk about an agent, it will first understand. And I understand in a manufacturing world by gathering information. Typically, we think about that coming from a sensor. I now understand the temperature. I understand oil pressure. I understand an RPM, a vibration. So, or a computer image. I understand that. Now, once I have contextual understanding, now I can reason. Now I can understand, especially if I'm getting multiple sensor inputs. The agentic approach is I can reason with this data coming in and understand and reason about what the context is on that particular situation, or in this case, on a manufacturing line. Now, with that knowledge, I can then start to plan action. What do we want to do? Now, I don't show it in this diagram, but at this stage is when we're really big about keeping the human in the loop on these systems. So even though they can run autonomously, we still want to keep checks and balances and a partnership with the human operators. And this here at the planning stage is an example of that. That the human, as the AI is making a recommended approach of what to do, it will build a plan that can be the human can review and approve it. Going on to the next stage, we can now act. Step 4 in here, or stage 4, is really the big difference. So even with generative AI, I can use the first 3 stages. I can get up to understanding, reasoning, and planning. But agentically, now I'm going to do something. The system, the agent, is going to take action. We can still keep the human in the loop. But remember, in all AI systems, they're probabilistic in nature. We have, uh, you can look at it that we think we may be right. I'll make up a number here, 95% of the time. But I still could be wrong 5%. So, we're going from a discrete computing world to something that's more probabilistic. So that means sometimes the agent will get it wrong. So we must, just like we do with our human operators, we must have stage 5 and the learning. How do we learn even if we did it right, reinforce that? If we did it wrong, we want to not reward that. We want to punish the system, so to speak. So this at a high level is really what we mean when we talk about an agentic workflow. So I said last year I did a talk, it was similar, and this was a model that I was showing almost 1 year ago. This was state of the art. This in this diagram here in the system that I'm showing, we had a digital twin of a specific pump. That digital twin was working in collaboration with an AI predictive failure system. It would monitor the vibration data coming in or the pressure data. In this case, it's water pressure, monitoring the flow rate. And based upon the changes in that flow rate, the system can then predict a failure. And then what we would do is, oh, I have a failure coming. Now, because I have generative AI in here with a large language model, I know how to, something we call RAG, retrieval augmented generation. I can go get my private data. I bring it into that agent. And the key was on the right side of this diagram, we would then package it up and notify a human operator. So the maintenance engineer or the operator, we would give them information and then they would go address the problem. That was 1 year ago. Today, the same system, we're not necessarily getting rid of other systems. We are augmenting them. Just like what we augment our human operators, we're augmenting that previous system. So we still get that information coming in place, but now what I'm doing, I'm adding this. I'm going to put in an agentic AI system to augment my predictive system. So if you follow the diagram here, we go from having a Gen AI maintenance agent that was in there previously. It sends a list of prioritized remediation actions. An agentic AI agent now picks it up. And in this case, I'm just calling it a technical assistant. The tech assist is there. And in this example, it is autonomously going to take 3 actions. The first one, it's seeing, oh, this pump is having a pressure problem. It's going to fail. I can't get it replaced for a while, but I know because remember, I have understanding and reasoning. I know I can reduce the RPM on the pump, reduce the flow rate, hopefully extend the life a few days or a few weeks until I can get the replacement in. Then the agent can go through to say, look, I know this pump needs to be replaced. I will autonomously go place the order. And then the third action it will take is then it will actually schedule it within the CMS for the human. And then at the top of that, and it still keeps the human notified. Now, there's a note here in the lower right of this diagram that's important. And it says, hey, how is this different than a traditional rules-based engine that we would have in the past? The difference is this agent wasn't necessarily programmed explicitly for the actions it took. The reason it understood to take the actions is because of the contextual understanding of these new AI-based systems. It understands, it reasons, it knows the plan, and based upon that, it then takes actions. And sometimes, and by the way, this is why when we get into the little bit more of the details later, this is why having guardrails, knowing how to use certain templates, knowing how to fine tune a model, knowing how to use RAG, there's certain things that we can do to sharpen the focus to make sure the autonomous actions it does take is well within a well-defined solution space. Because in the world of manufacturing, we can't have a machine just going off and arbitrarily saying, oh, I'll just shut the pump off now and then wreaking some other havoc in the system. It has to understand the overall workflow. So this is an example of how we go from a world of predictions to autonomous action that's dynamic and adaptable. All right. So what we see emerging are several different designs that are starting to come into the marketplace that we're all experimenting with. And what I wanted to share with you is we have a really good understanding of industrial IoT, but what we want to start to get the understanding is if I wanted in that last example I showed you, if we want to start to build that and we want to deploy something like that, how does that mesh architecturally? How does that all come together? And so before we go into the actual integrated architecture, what I want to share with you is a couple design patterns first. And so I want to just share with you 4 agentic AI design patterns, and they have varying types of capabilities in here. The first one is what we call a tool use pattern. And by the way, there's always a mixing and matching of these, but these are the macro level ones at an atomic level that you can think about because they do have very discrete actions of what they do. The first design pattern is called a tool use pattern. And in a tool use pattern, this is where the agent autonomously goes out and it seeks external tools, resources it was not initially programmed to do. Now we'll talk about it in a little bit, but there's a protocol relatively new, so a little over a year old now. It's called Model Context Protocol. And it is the key protocol that's really enabling this to happen. And I'll show you an example of how MCP is used. But this is one of the most powerful elements of this. In the old days, we used to have to hard code all these RESTful APIs and figure all of that out. And now there's different ways we could start to manage system level interfacing, particularly interfacing into models, how we can use MCP. And that's what enables the tool use pattern to go out and to look at these several and seek out data sources in other systems. The next one is the multi-agent pattern. And the multi-agent pattern is exactly what it sounds like, that we start thinking about beyond the agent. If those from the software engineering world, if you're familiar with microservices architecture, I actually draw a lot of correlations to this design pattern, a multi-agent pattern. If you So the analogy becomes each agent becomes like its own microservice. So there's a really good analogy, and a lot of the design principles from multi-services or a microservices architecture apply equally well here. The reason it's really relevant, when you put this collection of different agents, what they start to form are different types of workflows. And what's really starting to change in the way we think about applications, we're not really thinking about applications per se. We're thinking about the workflow, and then what agents would I need to drop in to help augment the human to execute that workflow. So this is really an exciting area that's emerging for us in the AI fields and industrial IoT and software engineering. This concept, this philosophical shift from apps really into workflows. And then two more design patterns I'll share with you. The next one, number 3, is a reflection pattern. That this is where you actually think of having two separate LLMs, or you may have two separate models, not necessarily two separate LLMs. You could have one LLM and then another, what we call a critic, that will understand and evaluate the output of the LLM. The reason we do that is, think of in this example, agent B being the conscience. Agent A acted, agent B becomes the conscience, and to say, was that right? And so this is part of that closed loop learning that we're putting in here. And then the third one is when we have planning actions. And sometimes you'll see the planning pattern. Sometimes we call it a PEC, a planning executor critic. There's actually a third component of this where an agent, just like what I showed you in that wheel diagram, there is a planner that understands reasons, plans. There's a agent that will then execute, and then another agent that will at the same time critique its output, and it checks not only the output but the result. And you can see these patterns, they can be mixed and matched, and there's hybrids that evolve, but these are some of and there's some other ones, but these are the 4 big pillars that I say that when we think about tasking and designing agentic AI systems, what it starts to look like. So let me give you a design pattern. I'm not saying, please don't take that this is the only way of doing it. There's many, many different ways. And by the way, on these design patterns, there's a lot of decisions that you need to make about the infrastructure environment. And what I mean specifically by that is making a decision and understanding how much of agentic AI or even generative AI actions will I take fully at the edge, or what actions can I take when I execute something up in the cloud. And the big difference, and many of us are very aware of this problem, but it's always about latency. Things that are mission critical, that you have a very, very low tolerance for latency, we try to push that as close as possible to the incident or to the edge. And then the things that can tolerate a non-deterministic nature of latency, that we can push up into the cloud. And the reason we want to have these, a couple different reasons, is one, the latency is an issue, but mission critical safety systems, we want to minimize the opportunity for failure. And so we try to keep those on the edge. This helps for resiliency purposes. And then those things that are not necessarily mission critical, or things that can tolerate a difference in the latency. We'll push that into the cloud. So that being said, what I'm showing here in this particular design pattern fuses those previous couple slides into now we're going to start walking through what does it actually start to look like in practice. So we think about the edge. I'm going to go from bottom up on this piece is where we look at having PLCs, RTUs, what I'll call and everything wrapped up around the protocols. This is the sensing side of it. This is where I'm bringing control signals. I'm bringing sensor data, and I'm bringing it in, pushing it out. And then I may be communicating all that with an edge gateway over another protocol of MQTT. And by the way, one of the things that we'll see it in a few minutes, one of the things we're experimenting with and starting to contemplate is, remember earlier I was talking about that MCP, Model Context Protocol. Now, even though we already had 50 different protocols on the manufacturing floor, and yet we have another one, but we do want to explore how we can start to take MCP over MQTT to talk to systems out on the factory floor. So that's an evolving component that we're looking at. And then I already talked about what in this model here of local inferencing, and you'll see a new term here that I haven't spoke to, where most of us are now familiar with large language models. This is a small language model. And or smallish, maybe that's a better word, because in this context, small usually means less than 7 billion parameters. Still pretty big, very, very capable. But they're smaller in size, computationally faster, and when speed matters, that we can have a very fine-tuned model on a 7 billion parameter item, and we can keep that on the edge. But now going above this, so what does the agentic AI core start to look like? Well, this very much matches that diagram that I was showing you. And you'll see this theme carry out, by the way. We see agents for understanding, pulling understanding sensor data. We have a reasoning agent that uses an LLM with RAG and a graph ontology. Graph ontology, think of it as your knowledge graph, the understanding the nodes and the contextual relationship between the nodes. So when I take RAG, which accesses my private data, and I have a well-defined graph ontology, now the system in collaboration with the LLM can reason. Then using the LLM, we can use it for the planning agent, then the acting agent to actually transmit, to tell actions to take place. And then lastly is the learning agent. And I could spend a whole session on any one of these blocks, by the way. But the last block here is when we're looking at actually my acronym's wrong. It's reinforcement learning human feedback, RLFHF. But that's where we keep the human still, even in these systems, having human expertise is still very, very valid. And then moving upstairs to this, really making it a holistic system that we want to have the interconnectivity to understand and have access to doing broader enterprise integrations, making sure we're aligned to security and governance. And then the types of systems we would want to be able to talk to is the manufacturing execution systems, the ERPs, or your CMMS that we may have. So, and I know it's a very simple diagram, but it kind of gives you the flavor of the stacks, of what that stack would look like on the factory floor. And I'm going to skip this slide for a moment, but this just gives into a little bit more detail on this. But now we're kind of building up the story. So I've shared with you guys the design pattern of agentic AI. Then I showed you a design pattern. Now let me start to show you what does something look like more in practice. What are the pieces we look at? And remember earlier, I also said that these design patterns that we're defining, they're applicable in a variety of different industries and enterprises. So I'll walk you through an example. So what I'm showing here in this kind of blue and yellowish color, this is some technology that we've developed at KMS, and we call it VLOX. It's an AI orchestration layer for agents. But what it is able to do, and it integrates and it facilitates role-based processing. So the idea with a system like this is not to replace your existing capabilities. Remember, I was showing that in that earlier examples, but how do we augment? The difference becomes the new agentic AI systems now start to get what's really, really important is they have contextual understanding of a production line or an entire factory. They do that because they are connected out to physically to understanding information from machines and understanding and connectivity to those enterprise systems. And we were talking, I said I would share a little bit more about it. Like we talked about this new protocol that we've been using for the last year, Model Context Protocol. Originally, it was designed so we could easily, quickly interface to different types of models, but now we're finding we can extend it to actually become part of the system interface to many different systems. And it works extremely well because you don't have to go to this huge API building. If somebody's MCP compliant, it makes it not quite plug and play, but the way I kind of like to describe it, MCP, our objective is what it will emerge to become is how USB really made device interconnectivity easy. That's what we're hoping and striving for with MCP. And we're already seeing a lot of initial successes with that. So describing this just a little bit more detail, that up here we have a manufacturing team. We have different sets of role-based, of a plant manager, an operator to the line supervisor, interfacing to their agentic AI system. And what it's able to do, it understands workflows. So what's different about this is when you look at this diagram, what you can't clearly see or what's not clearly evident, you don't see an application per se because it's the system itself is dynamic, that it is a function of the types of agents it has access to. So what I'll call, we almost want to start thinking instead of the concept of applications, we want to think about personalities that the system can adapt to the personality for the plant manager. I understand what a plant manager needs. It's different than what a line operator needs. And so this is where we're getting into some really new breakthrough thinking about moving away from that concept of applications, but thinking about a personality or personalization of these workflows. And that's what these systems are starting to move into. So because of this interconnectivity to the other systems, machines on the floor, the enterprise systems, we get deep contextual awareness. We understand, we being the AI in this case, what's happening across the entire footprint. And the idea is we're not trying to replace humans. As a matter of fact, if you look in the diagram here, we show it how the humans and the AI are working in concert to achieve a better outcome. And we want to do that by giving them higher accuracy and fewer rework cycles on here. Now, there is a lot of work that gets done to make sure that these systems are not running entirely open loop. What I mean by that, LLMs are unbelievably amazing, unbelievably smart, but we want to make it contextually aware of our specific environment, my documents, my machines, my production output, my ERP, my production schedules. That's where in this lower corner here, this project contacts RAG database, understanding how to get information and have access to it so we can have the humans do ask and query and still even just use prompt based. Even though we're talking about agents, this system still supports the idea of humans interacting and asking questions. And just ending on this one is we're really talking about amplifying. We're not looking to replace. This complements our humans, that working better together, we can speed up throughput, and the hope and the desire is to reduce the overall downtime and without adding more and more systems to help try to address that. So how do we move forward with something like this? Well, there's nothing magical about this, but you do want to think about it. And the big takeaway from this particular slide is really about we want to think in the terms of a crawl, walk, run. If you remember in the beginning, I was talking about 90% of projects fail to make it into production. When you look at the data, the big reason that becomes is they didn't follow a an approach to actually solve the production problem on the floor or the problem that may be in that particular enterprise. So we want to go through this preparation phase, working on how to select your hardware, making sure we select the right data sets. We pilot it, and the pilot must be based upon a real world problem. Don't become the solution in search of the problem. And then we go into phase three, which is then we start scaling it. But the whole idea is crawl, walk, run as we go up into the system. Now, there's a lot of challenges that emerge, and I know there's a lot of detail, and we'll have a QR code at the end that you can take a screenshot of it and download these slides. But there's a lot of different elements and things that we have to take into account. And the one that I really want to point out of all of this is the security one. When we talk about IEC 62443, that whenever a system and there's data being written back out to a PLC, when we're talking about a system issuing controls or a control feed or changing how the machine behaves autonomously, this is where the thing that we've got to be right. We have to have the right guardrails, and we need to make sure. So if there's an area, the biggest area that you want to make sure is right, is the right guardrails, particularly if you're going to make it more autonomous, that these are expensive machines, they can be dangerous, and we don't want to have a bad situation evolve. And then I already talked a lot about this human in the loop, security compliance, and making sure we have good logs and legacy fallback. That we want to be able to know that if we get in a bad spot, or we can prove what happened, why logs are important. And then where I want to end on the session is just another case study. There's a link. You can read this paper that was published. I really liked it. But this fits right within the model that we're talking about. This is for a ceramic manufacturer where they have, you can see all the elements we've been talking about, a sensing agent, a reasoning, an action agent. And they have an interesting thing that they did called a federated learning. And with the federated learning, what they enabled a distributed, a decentralized approach where the models could learn. And so that makes it very, very scalable. So when they deployed this system and started using it, what they saw was a significant improvement in understanding the remaining useful life of equipment, radical or material improvement in unplanned downtime. OEE from 74 to 83%, that's a huge movement. And a 19% reduction in MTT, maintenance between repair times. So you can see when properly deployed, these are really, really important elements, can have a very material impact. And so that just brings us to the end, everybody. I really appreciate you letting me share a little bit about the problem we're trying to attack, shared with you how we start to fuse our industrial IoT systems and modernize them with an agentic AI approach. And then we shared some design patterns and a case study where the results were realized by the folks that executed that. And then I said, lastly, there's a QR code. So if anybody wants to take a screenshot of that, go ahead and you can download and have access to these slides. So with that, I want to say thank you. And Kevin, I hand back to you, my friend.